Good morning. So now, today we will have two major discussion. Okay. So the first one, so both of the discussion is about the fluid in rotational motions. The first one is about the viscometer, and the second one is about just the plain tank. Okay. So before I start, do you have any questions from yesterday's class? Any questions from yesterday's class? I think that was fine, yeah. And I think you can also did the quiz very well. Now we're gonna start today's discussions. So first, in our first case, we have a tank, okay, and another cylinder, okay. So this cylinder is a rigid cylinder inside a bigger tank, okay. Maybe I should draw it a little bit longer. So between these two cylinders, we can put fluid. So this is the fluid. Usually what we put here is liquid, yeah. So this is the fundamental concept of viscometer. If you ever use a rotational force viscometer, such as Brookfield and so on. So this is the fundamental concept of the rotational force viscometer. So we put fluid here in the tank, and we have a rigid smaller cylinder in the center, and then the big cylinder, the big tank, rotating. So the big cylinder is rotating. Counterclockwise. Okay, so the outer cylinder is rotating counterclockwise, while the small cylinder is in stationary. Okay, so if we look at this case from above, we will get this picture. So this is the small cylinder, this is the bigger tank, and this is the fluid. Okay, the outer cylinder rotates to these directions counterclockwise with angular velocity of omega O, okay, omega outer, So this is the angular velocity, yeah, for rotation. What else? Okay, the diameter of the inner cylinder is Kr, and the diameter of the outer cylinder is capital R. Okay, so what we want to know is what is the velocity profile of the fluid inside these two cylinders, in between these two cylinders, and what is the torque? What is the actually what we want to know is not the momentum flux distributions, but the torque. Yeah, the torque. What is the symbol for torque? I think this one. What is the torque to rotate the outer cylinder? Okay, so when we have this kind of situations, it will be very difficult if we want to use the shell momentum balance. So it will be better for us to use the equation of change table. Okay, before we proceed, let's look at the velocity profile. Okay, when the outer cylinder is rotating counterclockwise like this, and the inner cylinder is in stationary, means that the fluid here, the fluid in contact with the inner cylinder is stationary as well. And the fluid in contact with the outer cylinder will rotate with the angular velocity of omega 0 as well. Okay, so the velocity profile of the fluid looks like this. Okay, I think that's clear. Now let's see the appendix B, table B5. Sudah? Oh yeah, okay. Okay. Oh, actually, if you want to know the velocity profile, the table that we should look at is the B6. Yeah, the B5 is for the momentum flux distributions. Okay, B6. We have cylindrical coordinates here, B64, B65, and B66. Okay. From that table, we know that we're gonna use bisa digedein sedikit, sorry saya nggak bisa lihat dari sini. Okay. Okay, thank you. Yeah. So we're gonna use the second equations, the one with phi theta. Okay. Why do we use that equations? Because the only motion that we have is to the theta directions, rotational theta directions. Okay. We don't have motion to the z directions because the fluid is not going up and down inside the cylinder, and we don't have the motions to the r directions. Okay, so what we have is only rotational motions. Therefore, we only use the second equations. Okay, from that table, let's look at the left-hand side of the table. Okay, the first term, dou phi theta dou t, that's 0 because everything is in steady state. Next term, phi r dou phi theta over dou r. Once again, we don't have phi r here, so that's 0. Yeah. Next, phi theta over r, so on. Phi theta, we don't have phi theta, means that term is also 0. Next, Vz, dou phi theta over dou z, we don't have Vz, that's 0. Next, phi r, phi theta over r, we don't have phi theta. Sorry, we don't have phi r, that's 0 as well. Okay. Next, we have equation on the right, minus 1 over r, dou p over dou theta. Okay. To the theta directions, yeah, means that at similar r and at similar z, we don't have the pressure gradient. Okay. At similar z, similar height, we don't have the pressure gradient. Okay. So dou p over dou theta is 0. Next, mu dou over dou r, 1 over r, dou over dou r phi theta. Okay, we have that term. That term has a value. Okay, so we keep that term. Wait a second, I will write it on the whiteboard. Yeah, just give me a second. That's mu dou over dou r, 1 over r, dou over dou r phi theta. Okay, next term, 1 over r square. Okay, 1 over r square, dou square phi theta, and so on. We don't have phi theta, that's 0 as well. Next term, still dou square phi theta, we don't have phi theta, that's 0 as well. Next, 2 over r square, dou phi r over dou theta, we don't have phi r, so that's 0 as well. And the last one is rho g theta. Okay, we don't have gravity to theta directions, we only have gz here. Okay, so this term is 0. End up, what we have from the table is only one term. Okay, only the mu dou over dou r, 1 over r, dou over dou r phi theta. That's all. Okay, now let's go back to the screen, to the whiteboard. Okay. Okay, now to solve this equation just like yesterday, just do it one by one. Okay. First, the mu, move it here, can be cancel out. Okay. Next, sorry ya. Do the first differentiation. We got 1 over r, dou over dou r phi theta equal to C1. Okay, the first differentiations that equal to C1. Okay, next we have dou over dou r phi theta. What we have here? C1 times r. Okay, and then next integrations we have r phi theta C1 r square over 2 plus C2. Okay, so our phi theta equations is C1 r over 2 plus C2 over r. Okay, so we have two constants here, means that we need two boundary conditions. Okay, we need two boundary conditions. Our first boundary conditions is at r equal to something, phi theta is something. Okay, and the second is similar. If you look at this case, so for the velocity boundary condition, we can look at these positions and these positions. Okay, so at radius equal to kr, our phi theta is 0. Why it is 0? Because this rod is not in motion, it's stationary. Okay, and the second boundary condition is at r, at radius equal to capital R, here, our phi theta is omega 0 times r. Okay, please remember that omega 0 is the angular velocity. Yeah, that's the angular velocity. So if we want to have a linear velocity, phi theta, yeah, linear. So we need to multiply the omega outer with the radius. Okay, so that's the boundary conditions, and then we must put or substitute this boundary condition to these equations. That's a bit tedious. Yeah, that's a bit tedious. So I will skip that. You can do that. It's very easy but tedious. We have limited time. So at the end, I already calculate what is the velocity equation. So at the end, what we have is omega 0 r Okay, so at the end, after we substitute these boundary conditions to the equations, we will get this equation for phi theta. Okay, a bit tedious, just try to do that. Okay, yeah, so our first mission to get the velocity profile is accomplished. Okay, now our second mission. Okay, our second mission is to understand or to know what is the torque to move or to rotate the outer cylinder. Okay, if you still remember torque, the equation for torque, or equations, okay, a second, let me get back to the Gmail. Turn on microphone. Okay, oh, viscosity, yeah. Zephania, where is the viscosity? Okay, so actually we have it here, yeah, but then kedengar suara saya kan? Yeah, but then just like I said, when we have complicated equations like this, we solve it like one by one. Okay, so first I move the velocity to this side. Yeah, velocity 0 divided by velocity will give me 0. So actually it's, I can just erase it like this. Okay, is that clear? Okay, thank you. Yeah, so excuse me, get back to the, okay, another questions. Okay, okay, please, Fauzan.
Miss, can you repeat why the pressure gradient is zero?
Okay, okay, okay. Yeah, I can. So basically, what we have in that equations of motion stable is dou p over dou theta. Yeah. So what is p? P here is uh, the pressure of the fluid. Yeah. You already understand what is p. Okay. So here, okay, yeah. So actually we have three components of P. We have dou P over dou theta, we have dou P over dou Z, and we also have dou P over dou R. Okay. Now, if we look at dou P over dou theta, okay, means that we look at the change of pressure at various theta, okay, at various theta, but in similar r and at similar r and at similar z. Okay, what is the what this condition looks like? Okay, when we have various theta, okay, when we have various theta, means that we look at the pressure here, 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 yeah, yeah. All of these dots have similar radius. Okay, have similar radius, just at different positions. Okay, this one might be at 30 degrees, 60 degrees, 70 degrees, and so on. Yeah, so basically ada suara ting ting. Saya, excuse me, bukan. Kok kayak ada, is it Michael? Okay, sorry. Panggit just called me. I don't know why. He knows I'm teaching here. Okay, yeah. Okay, so basically what we have here is the pressure at different theta position. Okay, theta is like the sudut, yeah, sudut from this, okay, degree. Okay, so at this position, the pressure should be the same. Okay, pressure should be the same because it is at similar level, yeah, at similar level, just at different theta, just at different, hanya ada di sudut yang berbeda gitu. Jadi kalau misalnya kita punya seperti ini, cuman lihat miring sedikit, tapi radius and ketinggiannya sama, ya. Okay, Fauzan, is that clear? Yeah. So at similar height like this, similar radius, so your pressure should be the same. So you don't have dou P over dou theta. Yeah. Okay, thank you. Maybe another questions?
Unrelated, but the absent in 6 is not yet open.
Sorry. Always forget.
That's why I'm
Give me 30 seconds to do this, okay? A second. Okay, I can find. Okay, you can fill the attendance until 12 today. Okay, until 12. Okay, yeah. So let's move. Still have another question. P change with respect to R and Z. Okay, that's interesting. Yeah. So does the pressure change with respect to the Z and R? Okay, to the Z. Okay, to the Z at different level like this. Yeah, at different level. When the fluid is rotating like this, yeah, actually the P is different. The P is changing. Okay, we will look at the change of pressure to the Z and to the R direction in the next case actually. Okay, so Fanya, if you may, just wait until the next case. Okay, so in the next case we will talk about this. Yeah, so maybe I should continue. Yeah. Okay, so we are at the torque here, at the torque. Okay, so basically torque is the force times the lever arm. If you still remember, I hope you still remember what is torque. Okay, so torque is actually the force times the lever arm, and we know that the force, it comes from the F divided by A equal to tau. So the force is actually the surface times the shear rate. So to get the torque, we need to know what is the tau. Yeah, what is the momentum flux distribution? Okay. Now that brings us to table B5. If we want to know what is the tau, what is the momentum flux distributions, yeah, intuitively we will look at the table B5. Okay, we look at the table B5 here. Okay, we look at the table B5. Nah, okay, the only tau that we're gonna have is only tau r theta, yeah. So the momentum to the r directions, because we have movement to the theta directions, yeah, tau r theta. So that's the only tau that we're gonna have. Okay, so when we look at the second equations there, everything on the left is 0. Yeah, everything is 0. Okay, then when we look at the equation on the right, dou p over dou theta is 0. 1 over r, dou over dou r squared, tau r theta, we have a value. Next, tau theta theta, that's 0. Next, tau z theta, that's 0 as well. Next, tau theta r minus tau r theta, yeah, that's 0 basically, yeah, that's 0. And next, rho g theta, okay, rho g theta. So what we have here is only 0 equal to minus 1 over r squared dou over dou r squared tau r theta. Okay, so basically that's what we have. Bisa kembali lagi ke whiteboard sebentar? Yeah, okay, yeah. So this is what we have. If we want to solve this equation, yeah, 1 over r squared go to the left, means disappear. Okay, so we do one integration that will give us constant equal to r squared tau r theta. Okay, now if you look at this equation, can you solve this equation? Can you find constant? Yeah, I don't think so. This equation is merely just information. Yeah, it's merely just information, says that the tau times r squared is constant. Yeah, but even if you put boundary conditions, even if you have boundary condition, you cannot solve this equation. Okay, so how to get the tau if we cannot solve this equation? Yeah, that's interesting. So how to get the tau, okay, is by move backward from the velocity, or we can go to table B2. Is it B2? I think it's B2, yeah. Table B. Oh, no. Sorry, I think that's B1. 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 Okay, cylindrical coordinates. Here we have several equations from for the tau. Okay, usually what we generally know, tau, just like when we have Cartesian coordinate, we know that tau x, example, yeah, tau xz is minus mu dou vz over dou x. Okay, now that's for Cartesian. For the cylindrical, we also have the definition of tau. Let's look at tau r theta. Okay, B111. B111. That's tau r theta. Tau r theta is equal to minus mu r dou r phi theta over r plus 1 over r dou phi r over dou theta. Okay. The last term, dou phi r over dou theta, is 0. We don't have phi r. Okay. So that gave us tau r theta is minus mu r dou over dou r phi theta over r. Okay, now let's go back to the whiteboard. Okay, so basically to get the tau, we can move backward from the velocity. Yeah, we already got the velocity equation here. Yeah, we got the velocity equation here. We can substitute this equation here to the phi theta. To the phi theta, yeah, substitute everything here to phi theta and divide by r, and then just solve this equation. Yeah, dou over dou r from equations, then times r, then times minus mu. Okay, I think this is simple. Yeah, you just need to put this equation here, divide by r, and then do one differentiation. Yeah, so this one is differentiation. You will not do integrations. This is differentiation. Okay, and then times r times minus mu. Okay, it's easy to say, but when you do that, mathematically challenging. Yeah. At the end, what we're gonna have is tau r theta equal to, it's minus mu. Okay, minus mu times minus 2 omega 0. Okay, square r square divide by square minus 1 times 1 over r square. Okay, so at the end, after you substitute this equation, the phi theta equation here, and then do differentiation times the r times the minus mu, at the end, this is what you will get. Okay, we have minus minus. I just erase it and put positive. Okay, so if you want to calculate the torque is the it's not the force, yeah, but the torque to rotate the outer cylinder, because in our case the one that's rotating is the outer cylinder. So what we want to know is the torque to rotate the outer cylinder. Okay, for the torque at the outer cylinder. Yeah. So when we calculate the force, the surface area must be the surface at the outer cylinder. Okay, the surface when the surface where the shear force acted on the outer cylinder. So the surface is 2πr times L. L is the length of the cylinder times the torque. Okay, times this thing, yeah. Okay. Times this thing. Just put everything here, and times the lever arm. Yeah, the lever arm is the distance between center and the surface that we want to observe. Okay, at this case, the surface, the lever arm is R. Okay, distance between the center and the surface that we want to observe. That's R, because it's outer cylinder. Okay. So at the end, what we will have, maybe I should add another one here. Torque is 4 V mu L omega 0 R square. Okay, square minus 1. Okay. This one is constant. Depend on your equipment. Okay, how big your equipment. And this one is also constant. Oh, sorry. The mu is not. Okay, so actually this part is constant as well. Okay, so if you want to know what is the viscosity of the fluid that you put on that viscometer, you need to observe, or not you, but the equipment will observe what is the angular velocity and what is the torque needed to rotate the outer cylinder at that angular velocity. Yeah, using that data, they can calculate the viscosity of your solution. Yeah, so that's the fundamental concept of rotational viscometer. Okay, yeah, I skip a lot of mathematical things here, but I hope you can do that by yourself, because it's just substitution and differentiations. Yeah, that should be easy, but takes a long time. Any question before I continue to the next case? Question? Still have any question? Okay, ada question ya. Okay. Okay, what is K? Okay. Langsung aja sampai sini ya, nggak usah ganti. So, sorry ya, maybe it's not clear in the beginning. K is here. Yeah, so the radius of the small cylinder inside here, the small cylinder inside is KR. Okay, it's KR. So that's where the K come from. Yeah. Yeah. So basically K is not 1, yeah. K should be less than 1. Yeah. If K is 1 means that the cylinder inside is in the same size with the tank. That's impossible. Okay. Good observation, Fauzan, yeah. More question? No question? Okay. Give me 1 or 2 minutes. I will erase everything here. Okay, I'm sorry, I cannot go like move fast enough. So maybe we should extend the class until 10, a bit more than 10, yeah, maybe 10:05 or 10:10 or 10:10, yeah, if you don't mind, okay? But if you have another class or if you have something else to do, just tell me, okay? Okay, so for our next case, we have just tank, yeah, just one tank like this without any cylinder inside, just tank. And then inside this tank, we fill the tank with a fluid, with a liquid. Okay, so in the beginning the position is like this, yeah, the liquid is still like this, stationary. Then somehow we rotate the cylinder, yeah. Now when we rotate the cylinder, what will happen to the liquid inside? Okay, what you don't have your lab tech yet, yeah, you don't have your lab tech yet, but you have your fluid mechanics. Hopefully you can understand, okay? So when we rotate the outer cylinder, okay, what will happen to the fluid is it will create a vortex like this, yeah. So when we rotate the tank, the fluid will form a vortex like this. In this case, let's say that we rotate the cylinder counterclockwise like this, yeah, with omega 0 as well, okay. The height of this vortex is z0, just say z0, okay, and the radius of the tank is capital R, okay, and we can draw example, yeah, the coordinate z and r like this, okay. So when we have this kind of situation, we know that the pressure here, the pressure at the surface of the vortex, this must be P0, okay, P0, which is equal to atmospheric pressure, yeah, P0. This one is the pressure at the surface, okay, and the surface of the fluid inside here, okay, the pressure of the fluid inside the vortex will be a function of R and Z, okay. So the fluid will have varied pressure at different height and also at different radius, okay, but it's not a function of theta, yeah, it's not a function of theta, just like what we discussed in previous example, okay. So the pressure is the function of R and Z, okay, but it's not the function of theta. Now the question is, can you determine what is the equation that might show us the profile of the liquid height, okay? So what we want to know is what is the profile of the liquid height, okay? We might think, oh, out of nowhere, how could we determine the liquid height? Yeah, out of nowhere. Usually we only want to know the velocity, momentum flux, or force, or maybe torque, still related, but how about liquid height? Okay, it's a bit different. Now let's look at the table B. Wait, B6. Yeah, let's have a look at table B6. Okay, bisa tolong digedein? Ya, makasih. Okay, so intuitively, we always use, until now, we always use only one equation. Okay, and because in this condition, we have phi theta. Yeah, we have phi theta, velocity to theta directions. We will intuitively use that phi theta. Okay, we will intuitively use that equation. Now, if you look at that equation, yeah, if you look at that equation, everything on the left is 0. Yeah, and on the right, what we're gonna have is only mu dou over dou r, 1 over r, dou over dou r, r phi theta. Everything is 0. Okay, everything is 0. Okay, now let's have a look at equation B64 and B66 as well. Okay, from equation B64, let's look at the equation one by one. Dou Vr over dot t, that's 0. Next, Vr times something, Vr is 0, we don't have Vr. Next, phi theta over r, dou Vr over dot theta. Dou Vr over dot theta is 0, we don't have Vr. Okay. Next, phi z something something, phi z is 0, we don't have phi z. Next, what we have is phi theta square over r. Yes, we do have phi theta square over r. So from that equation, we have rho minus rho phi theta square over r equal to, now let's have a look at the equation on the right. Minus dou p over dou r. Yes, we do have dou p over dou r. Okay, and the rest we don't have. We don't have the rest of the equation. Okay, we don't have Vr, we don't have dou Vr, we don't have dou Vr over dou z, we don't have dou phi theta over dou theta, we don't have. And we also don't have the rho gr. Yeah, we don't have rho gr. So from that equation, we got something. Now from the last equation, B66. Phi z over dot theta, that's 0. Phi r, 0. Phi theta over r, dou phi z over dot theta, that's 0 as well. Phi z something something, phi z is 0. Okay. Next, minus dou p over dou z. Yes, we do have that. Dou p over dou z. Then everything with mu, we don't have everything with mu there because that's related to the phi z. We don't have everything with phi z. And the last one, we have rho gz. Yes, we do have rho gz because we have gravitational force to the z directions. Okay, that's positive rho gz. Okay, boleh kembali lagi ke papan tulis. Okay, ya. So from this equation, we have 3 equations from the table. This one from B64, this one from B65, this one from B64, and this one from B66. Okay, these equations show us, if you still remember, this term is centrifugal force. Yeah, this equation shows us the effect of centrifugal force, yeah, on the pressure gradient. Okay, so the pressure is varied to the r direction, to the radius, because there is a centrifugal force. Okay, maybe this can answer Fenya's questions, yeah. So this is centrifugal force. Okay, because we have centrifugal force, so the pressure will vary to the r directions. Okay, next to the z direction, yeah. To the z direction, we can look at this equation. that the pressure is varied to the z directions because we have, what is this? Hydrostatic, yeah? Hydrostatic. Okay, because we have hydrostatic and we have centrifugal force, then the pressure will vary to the r direction and to the z direction. Okay, but to the theta directions, the pressure is constant. Okay, yeah, I hope it's clear until now. Now, if we may continue, let's try to solve this equation first, the B65. Yeah, try to solve this. This will give us exactly the same equation as the previous example. It will give us the phi theta equal to C1R divided by 2 plus C2 divided by R. Okay, so exactly the same equation as we get from the previous example. Okay, so now what we need is the boundary condition. Okay, boundary condition 1 and 2. Okay, for the first boundary condition, we can say that at radius equal to 0, yeah, at radius equal to 0, the phi theta cannot be infinity. Yeah, so yeah, at the center of this system, the phi theta cannot be infinity. The phi theta should be finite. Okay, so that will give us, if we put r equal to 0 here, that will give us C2 should equal to 0. Okay. Now the second boundary conditions is at r equal to capital R, yeah, at the wall of the cylinder, at the wall of the tank, the velocity phi theta is omega outer times r capital R. Okay, so if we put things over here, we will get omega 0r equal to C1 r divided by 2. That will give us C1 equal to omega times 2. Yeah, and up we have phi theta equal to omega r. Only omega r. Yeah. So this is our velocity profile. Okay, so that's our velocity profile. Okay, this velocity profile will be used to solve the equation from B64. Yeah, if you notice that we have velocity phi theta over here. Okay, so we can substitute the phi theta here with omega r. Yeah, that will give us, sorry, yeah, I might rewrite the equation. Okay, substitute phi theta with omega r, we will have omega square r square divided by r dou p over dou r. Okay, sorry, it's not capital R, but should be just radius. At the end, we have dou p over dou r equal to rho omega square r. Yeah. So this is our pressure variation to the radius direction. And for the one to the z directions, we have this equation. Dou p over dou z equal to minus rho g. Okay, equal to minus rho g. Okay, now if you have a look here, we have dou p over dou r and dou p over dou z. Yeah, we can write this differentiation into its complete form. What is its complete form? We have d pressure equal to dou p over dou z times dou z plus dou p over dou r times dou r. Yeah, so you got this from calculus. Okay, from calculus. Yeah, the total pressure, the total differentiation, the total. So this one is like partial, what is it? Partial differential. What's it? Partial differential? Yeah. So this is partially to z, and this one is partially to r. Yeah, in total you have this total differentiation. Okay. Now we can substitute. So this one will equal to minus rho g. Yeah, dou p over dou z is minus rho g, dou z plus dou p over dou r, rho omega square r dou r. Okay, and we have to integrate these things. Okay, when we do integration like this, yeah, when we do integration, we'll have pressure equal to minus rho gz plus rho omega square r square divided by 2. Okay, don't forget the constant. Even though we have two integrations, two integration component here, yeah, but still we only need one constant, yeah, because we only do one times integration. Okay, one constant. So what is the constant? So the constants can be solved by using one boundary condition. Okay, so what is the boundary condition? Now let's have a look. The pressure is the function of z and r. Okay, so your boundary condition should be at z equal to something. Yeah, at z equal to something and r equal to something, the pressure is something. Okay, so now which pressure do we know? We know that at r equal to 0 and at z equal to z0. Yeah. Do we still have the figure? Yeah. We know that at r equal to 0 and at z equal to 0 to z0, that means this position, our pressure is the P0. Yeah, should be the same with atmospheric pressure. Okay, now we put the boundary condition to the equation. So what we will get is P0 equal to 0. Oh, no. P0 equal to minus rho g z0 plus 0 plus constant. Yeah, so the constant is P0 plus rho g z0. Okay? Now we put the constant back to the equation. Yeah, we put the constant back to the equation. We have that P equal to rho omega square r square divided by 2 minus rho gz plus P0 plus rho g z0. Okay, so basically this is our equation after we put back the constant. Okay, now I can move the P0 to the left. That will give me P minus P0 equal rho omega square R square divided by 2, and then minus rho G, we have Z and Z0, Z minus Z0. Okay, now we already get a glimpse of the height distribution. Okay, now let's have another look. Okay, at the surface of the fluid, yeah, the pressure is P0, means that we can say that this P minus P0 should be 0 because the pressure is also P0. Okay, equal to rho omega square R square divided by 2 minus rho G C minus Z0. Okay, finally we will get that Z minus Z0 equal to rho omega square R square divided by 2 divided by omega G. Okay, sorry, by rho G. So the rho is disappear, and what we have is only the G here. Okay, am I correct? I think so. Yeah. So at the end, we got the height distribution of the fluid inside the tank. Yeah, so the height distribution is like this, and it is a function of R. Yeah, so if you put different radius, the height will be different. Okay, because omega and the G is constant. Yeah, so it's only depend on the radius from the center. Okay. Okay, I think it's already 10 past 10, yeah. So maybe I should end the meeting today. And if you have question, you can write down the question on the MS Team in our channel, and I will reply to that question as soon as possible. Okay. Next week we will have exam on Tuesday. Yeah, please prepare and good luck for the exam. Okay, sorry I cannot answer question now, but please write the questions down on the Microsoft Team. Yeah, thank you.